So, hello, my favorite sixth grade classes. Hope you are having a great day and you enjoyed your day off. Today's lesson is on activity 15.1. We are almost done with this entire unit. So, as soon as you come back from spring break, we are going to start into our next unit that we will probably be working on for the rest of the year. Okay, so our agenda today, move me over here. Today is Thursday, the 2nd of April. Our agenda and our is going to be a bell work today first, and then the video lesson, and then you should do your activity 15.1 on Google Classroom. So for your daily work that is due today, the bell work and the activity page, as well as your PEEP vote, please make sure that you get that in. By the end of this lesson, you'll design and use a particle model to explain phase changes from a solid to a liquid and a solid to a gas. Please make sure that you are also doing your bell work and your assignments. They go on your attendance, and grades are going to start going into Infinite Campus this week. Okay, excuse me. Introduction and thinking. Based on what we have learned so far, what do you think happens to the molecules of a solid as the temperature increases? Also, do you think that molecules in a solid behave similarly to other solids? So is the molecular movement or the molecular behavior the same from one solid to another solid? Are there differences? Think about it. What do you think? So next, think of some solids with odors. How do you think odors from solids get into the air? And our last two things are what is a melting point and what is a freezing point. Okay, we're going to go right into the video lesson. And I am going to be stopping it a little bit as we go to give you some further information.
Hello, sixth grade. So today we are going to be looking at a couple of experiments. The first one deals with taking a solid and turning it into a liquid and then looking and see what comes back. We're going to demonstrate how this works with our particle models. And we'll go over that more in the lesson when we get there. But for the first part, I'm going to melt down some wax and we're going to make a new candle out of it. So I have a candle that the glass on it broke. So I just broke the rest of the glass off. And so I have a couple of chunks. What I'm going to do is I'm going to chunk this up into smaller chunks. And then I'm going to put it in my tin can. And then I'm going to melt that over my stove until I can apply enough thermal energy to give enough movement to my molecules so it goes from a solid to a liquid. So I'll see you in a second. Okay, so I cut it up into pieces with my board scraper. And so I have smaller chunks. Stop and think, why would it be better if I had smaller chunks rather than one big chunk?
Okay, why would it be better if we had smaller chunks instead of one big chunk? Also, isn't my dog cute? Okay, so we're going to go back to the smaller chunks and the big chunks when we finish this part of the lesson. All right.
I can apply enough paper. And so I have smaller chunks.
Cute doggy again.
Stop and think, why would it be better if I had smaller chunks rather than one big chunk? We're going to talk about that in a minute when we get to melting point. So I'm just going to throw them in here. And put that in zinc. And let's bring it over here.
Okay, when you are melting wax, you need to use what's called a double boiler because wax can be a flammable and it can also be something you can easily burn. So what you do is you put it in one container and then you put the other that container into another container. And it's called a water bath. Okay, and nice little practical thing. You also use this when you melt chocolate or anything that is delicate. So also in the can, it's a lot easier to clean because I'm not too worried about the can. But I would have to scrub the wax out of my pot. And yes, I know my stove is dirty. I didn't notice. Sorry.
Alrighty. That looks good. Whoop. Okay. That looks good. So we're gonna see how long it takes for this to melt. Okay, it has been about 30 seconds, and you can see that it's already starting to melt. Okay.
Had to go get a stirring stick.
Okay, so I've got a glass stirring rod, and I am just kind of stirring it around.
All right, pause. So while I am melting this, I am smelling the scent of the candle very strongly. It was a lot like when we melted the menthol. Okay, so the reason why is because that candle was scented. It's pine scented. And when the molecules are heated, we apply the thermal energy to them. Some of those particles from the scent, from the perfumes, get into the air and it moves through air currents of hot air and cool air because they move together. And that is what that is what takes the scent particles into our nose where we can smell them.
Letting it absorb that thermal energy. Almost done. Just a few bigger chunks left. Okay, while that is finishing, I am getting my stuff ready. Granola bar doesn't count. So I have a couple of paper cups, okay? And I have just some cotton string that I tied onto a pencil. And I'm gonna make this into my wick. Okay. All right, so my wax is all melted, and I know you can't see me, but this way you can see the stuff. And I have the cup, and I have the wick. I dip the wick a couple of times into the wax to make it a little bit more stiff when I pour the liquid wax in, and I had to trim it. Okay, so now I am going to carefully pick up the can because it does have some heat, thermal energy transferred into the can as well because it's metal. Okay. And let's pour it in and hope I don't make a mess. Okay, we just needed one. Okay. But now I'm gonna leave this to cool for a little bit. And the thermal energy that is inside the candle wax right now in its liquid form is going to dissipate out into the air. So when I touch the sides of it, I can really feel how hot it is. And when it gets to a certain temperature, that wax is going to freeze up again into a solid. Alrighty. Okay, so it's been a couple of hours and I have my candle that I made, and I had to kick my son out of the kitchen because he's trying to make his dinner and I needed to film it. So what I'm gonna do is I'm going to tear off the outside of the cup. Wait, you're running away now?
He's running upstairs to get his Nerf gun. Well, go back. Sorry. Hopefully I can edit that.
candle that I made, and I had to kick my son out of the kitchen because he's trying to make his dinner, and I needed to film it. So what I'm going to do is I'm going to tear off the outside of the cup. What, you're running away now? He's running away. Okay, and which is not overly surprising, we now have a paper covered candle. Okay. All right, I don't want to take the time. So what happens when the wax gets thermal energy? It liquefies, it melts. What happens when the wax loses thermal energy? It freezes into a solid.
And that's where my son shot me with his Nerf gun and missed. Okay, so here we have our particle model we've talked about. Now, we've talked about positive things and negative things about a model. Obviously, there's something big missing on this one. Can you guys tell me what it is? We are missing movement. Okay, so here I have my gas models, or sorry, here, well, bleh. Try again. Here I have my solid model. You can tell that they're all in a nice little grid. Okay, it's in a nice little compact form. They are only vibrating slightly, not even enough for me to draw motion things on. Here's my liquid. There's some movement, but the molecules like to stick together. Here I have the gas. This is where they're moving faster. They're hitting the sides of the container. They're hitting off each other. They're going out of the container. This one has its own form. This one takes on the form of the container. And this one doesn't even care. Okay, if it's open, it goes into it. So when I transform the wax from this state into this state, some of the perfume was able to turn into a gas. Usually it's done with an alcohol, and alcohol has an evaporation rate that is quite low. And those scent molecules go out into the air. Okay, freezing points and melting points. A melting point is the temperature that a substance melts at. It will always be the same temperature window. It's within a degree or two. A lot of it depends on just some very minute things that you don't need to worry about with the environment that you're in. And what's the air pressure? What's the ambient temperature? Blah, 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 blah. But generally, it's within a degree or two that the substance will melt. Now, the most common one we know is water. Water melts, or ice melts into water at 32 degrees Fahrenheit. Okay, but that's not the same as everything else. Okay, so wax obviously has a higher melting point because it doesn't turn into a liquid just at room temperature. It has to be higher than that. A freezing point is the temperature that a substance freezes into a solid, and it will always be the same temperature window, again, within a degree or two, that the substance will freeze or solidify. So wax has a freezing point of about room temperature. Okay, it took a couple of hours for my candle to freeze into a solid from the liquid state. Now, this is where we talk about the size of the pieces that were melting. Okay. When I have a substance that is melting, so if I took my wax parts and I put it on the stove and I put in my temperature probe, the temperature would increase until it hit the wax melting point, and then it would stay within a few degrees of that until everything melted. Okay, and then it would start to rise again. So the bigger my piece, the longer it takes something to melt. The easiest way that I can explain this is what I call, well, actually, there's two ways. Number one, the macaroni and cheese process. Okay. So when I'm making macaroni and cheese and I have to put in the butter to melt it after I cook the macaroni, don't know if you guys have done this yet. If not, go ahead and try it. Now, if I just put in that block of butter, it's going to take a while for it to melt. Okay. If I cut that big block of butter into smaller pieces, then it melts faster. Okay. This is because there is more surface area that heats up and gets more thermal energy, and it just melts faster. Another way is the snowball snowman comparison. If I have a snowball and I have a big snowman, they're both made out of snow. They're both made out of ice crystals. Okay. And they start to melt at 32 degrees. Which will melt faster, a big snowman or a snowball? The snowball will, because it's smaller. It has more surface area for its mass, and so it will take more or less time for it to melt. Okay, so when I want something to melt quickly, I want to chop it up into smaller pieces. Freezing point, same type of thing. The bigger the mass, the longer it takes for all that thermal energy to transfer. So if I want something small to freeze, like ice cubes, I put them in small pieces. If I have to put something big in to freeze, it's going to take a lot longer for it to freeze. Like if I put in a bucket of water to freeze, it might take a couple of days for it to freeze all the way. All right, let's go back to discussion. How do models help us understand phase changes on a molecular level? Okay, so this is what you're going to be doing in your assignment today. How does this model represent the characteristics of solids, liquids, and gases? Compare our three models. What is the same and what is different? Well, they all are made out of molecules. They're all moving in some way. Okay, and this is meant to be the same substance. What is different? Okay, as we've said before, the solid has its own shape and it's locked into a grid formation. Okay, that's why I can pick it up. The liquid, it's moving around. There's some movement. It takes on the shape of its container. Okay, and then the gas takes on its own shape. It doesn't have the shape of the container, especially if it's open. It has a lot more movement and there's a lot more space between the molecules. Okay, how can you use this model to explain melting and freezing? That's going to be another part of your assignment. Okay, so revisiting our predictions, based on what we learned so far, what do you think happens to those molecules of the solid as the temperature increases? They get more movement. They get more thermal energy, which results in more movement, which results in a higher temperature. Do you think the molecules in a solid behave similarly to other solids? Pretty much, yeah. They're always kind of in a formation. They always have their own shape, and they always have. You can pick it up. All that's the same. Now, does that mean that cake molecules are the same thing as ice molecules? No, not like the texture, but the molecules are acting the same. What is a melting point? The temperature window where a substance will melt. What is a freezing point? The temperature window where a substance will freeze into a solid. Okay, those are also properties of a substance. So they're not going to change depending on how big or small it is. Same thing with my snowman and my snowball. Okay, all right. I think that is everything today. So let's go visit your assignment. Okay, should be able to get your name and period. Describe what happened to the wax molecules throughout the experiment. Don't forget to include the solid part, melting point, and then the freezing point, or freezing parts. So 3 parts that you should be describing what's going on with those molecules. 3 points. Okay, ask you a question. What's the melting point and the freezing point of a substance? Now, in this part, this is where you are going to take our particle model, which I gave you, and you are going to teach me what's going on. Now, if you read this part with me, it says in this section, use the picture of the particle model to explain what's happening with the molecules in the different states of matter. Include descriptions of the movement of the molecules, what's going on with the thermal energy levels, and the way the molecules are arranged in each of the answers. You get 1 point for each of those parts on the next 3. Okay? So gas, liquid, and a solid. Nothing too bad. All right, I'll see you guys tomorrow. Easy assignment tomorrow. It's just a reading passage, and I hope you guys have a great day. Bye-bye.